Okay, let's do it. I want to spend one more lecture today saying, I think, not enough, but I feel like this is such a big topic of learning state representations. There's entire conferences on it and the like, but I hope to say a few more interesting things about it and make you think about it today. So the problem in my mind of intuitive physics is largely a problem of learning models, which is a problem of system identification, right? That's what the control people called it before, or lots of people called it before. And fundamentally, it's about taking input-output data from a system, right? So you're given data in the form of, I'll use this as my shorthand for the trajectory of data of u and y, plus a parametric model, typically a parametric model. Like we have been writing in state space form, for instance. I'll say it like this, these are my parameters. This might depend on the parameters too, okay? And the goal is to find the parameters, find my parameters theta to minimize my objective, my system ID objective. Some form of prediction error. I talked very briefly last time about saying there's a difference between a one-step error versus a long-term error. There's also, there's many different notions of error. If anybody has thought much about online optimization, the new way to talk about error in this setting would be as a regret, using the language of regret. But there's, basically I want to predict my y's given my u's, and I'd like to minimize my prediction error from the model and from the data. Okay, so again, I'll always try to start a little bit with some bigger picture, and then we'll dive into some examples and some details, okay? But, I want to appreciate this in the bigger picture of the things we've been doing in class. This is one of the problems you can ask given those equations, but it's actually, there's many questions we've been asking on those equations, right? So the slightly more exhaustive form of this, right, is that we could in general have dynamics that are time varying. They depend on state, they depend on u, they have potentially random inputs w. This is kind of all the things we've been talking about, and now we're emphasizing the parameters theta, same thing for y, can depend on all of those things. And by the way, in code, now you maybe appreciate finally, or well, maybe you still don't appreciate, but or like you might not like, but this set of things is exactly what we call the context in Drake, right? That's just why it's a structure, right? It has inputs, states, parameters, etc. It exactly maps to that picture of the world. And because sometimes you need all of them, sometimes you need some of them, it's just a structure, and that's why we write the code in that way. And what's nice is that, in this view of the world, in this dynamical systems view of the world, F could be a multi-body plant, F could be a neural network. Even more interesting, F can be a system, a diagram that has a multi-body plant and a neural network, maybe an inverse dynamics controller, all put together. And that, what I'm saying here still holds, and I can still describe it with some parameter vector theta that I search over. in order to solve some input-output identification problem. And in fact, there's a lot of work that's going on now where people are saying, what if I do identification over both the trajectory optimization and the model, for instance? Or there's lots of different combinations where thinking about F as being an entire diagram that has some autonomy inside it can be an interesting version of the problem. Okay, so think about this as my general palette of models that we're thinking about. And it's just kind of cute, maybe kind of nice to realize that all the things we've been talking about in class are just slightly different takes on what we're doing with that set of equations written in that form, right? Simulation, for instance, is just given x0 and a bunch of u's, solve for x, basically, right? You're given the parameters, you're given all those other things, but that's basically just solving for x by integrating forward. And planning is just, if I'm given some objective, maybe I'm given x0, solve for some trajectory like this, given x0 plus an objective, solve for x. Okay? Perception. Certainly in its state estimation form, is just, again, this is given now my parameters, maybe given my observations, my actions that I know I've put in, and my parameters, solve for x. And system ID is, given the data we talked about, solve for theta, right? But these are all very related problems. They must be very related problems making slightly different attacks at the basic governing equations, right? And I think sometimes we see them, we see all that. I mean, the particular way that you address this problem when y is a point cloud can leverage particular structure of those equations that you don't think about typically when you think about planning. But they really have to be the same thing, right? It's just a matter of specialized algorithms exploit special structure in the equations. Okay, and to some extent, I mean, there's been trends towards just thinking about, let's do gradient descent at this level of abstraction for any one of these chains. Okay, but I think it's very powerful to think about it in that bigger context. In fact, the difference between perception and system ID is sort of subtle. You could almost argue they're solving at this level of detail the same problem, because some people would say perception also has to estimate the parameters. To estimate the parameters, you probably have to estimate the state. Really, the only difference is the perception's trying to do it online, and system ID typically is done in batch, where you have a collection of data before that you're trying to estimate the parameters. Is that useful to think of it in that level? I don't know if that's just... But that's very important to me. That's very, this is partly why I think the systems view of the world, the dynamical systems view of the world is so powerful that I can apply my same reasoning about all of these different algorithms to systems that might just be a multi-body system, might have a neural network, might have a whole combination of them. And what changes is I change the model class. If I change F, basically last lecture, we said when F is a multi-body plant, Then there's special structure. Make system ID, or parameter estimation in this case, a least squares problem, at least some descriptions of it, a least squares problem. That's what I spent most of the lecture on last time, was telling you some of the details about how that plays out. And I really want you to think about this as there's a spectrum of models, right? Let's say this is my model spectrum here. And in some cases, there's very structured models with specialized algorithms. Right, and there's some very general models with more general and potentially weaker algorithms. Maybe necessarily weaker algorithms. Okay, so I'd say that, I guess, on the extreme part of this spectrum, if F and G are, let's say, linear models or tabular models, those tend to be the two cases that we can do the most. We can bring the biggest, most powerful algorithms to bear. Then that's like the extreme structure. We can understand everything, right? I'd say that the multi-body models are somewhere over here, right? I would say neural networks are, broadly speaking, deep learning stuff is here. It's not actually all the way to the extreme. I think there are, just big black box game engine kind of simulators are harder, right? Potentially, if I, for instance, have if G is a game quality rendering engine, and it's sitting on the GPU, and I can put doubles in and I get doubles out, but I can't really ask for any structure there. That's maybe the hardest case, the most general types of models. And all we can hope to do there are the kind of black box optimizations we've talked about. If you can assume that your models, if F is at least known to be differentiable, then that's a little bit more structured, and I can do gradient descent type algorithms, right? And if I go farther and farther, then there's more structure and more powerful algorithms. But you're making more assumptions, right? So the linear models cannot capture the complexity of the world, right? The models can capture a little bit more, but not all. They're not going to capture deformable things and fluid things very efficiently, right? So what I kind of want to do today is just walk a little bit more on this space and give you a couple more nice examples on that line. Some places, maybe even here, we can learn a little bit more. So there's some things about the system ID problem that are very clear if you go all the way here. There's some things that we're learning more and more on that end of the spectrum. Is the real world? Yeah, I guess the real world is on the right. If you're, the real world is not a mathematical object that I'm searching over. So I guess I wouldn't put it directly on the spectrum. These are the class of models, right? But it's a good question.
And also have a question for perception. So
yeah.
Can you give an example about the control in the equations? Like, in what case you would try to estimate x given u and y? Or like, why do you observe?
In the state estimation case, why is u observed? The standard state estimation, if I think in the simplest case, maybe be the Kalman filter, for instance, right? where it really explicitly takes in the actions that you've sent and the observations you get and estimates X, right? And I think more generally, that's true. It is true that a lot of times when we've talked about, point cloud perception or whatever, we haven't used this. We've been just learning static models from Y to some pose. But I think as soon as you think about that as a dynamical system and do a filtering kind of approach, then you would naturally bring in U. Great question. There's a bunch of different, entries on here, and I wanted to avoid listing all the things. There's a lot of shiny things up and down the axis here, and I don't want to just list them off. I'll just call out a few examples that I think I can say something interesting about. But people, I was looking to see if they're here, but there's a few people in the class that are working on like Lagrangian neural networks, for instance. They're an interesting point on the spectrum, and there are many, many entries. Okay, so multi-body can't do everything, right? We certainly, I'm the first to admit that. So the multi-body parameterization, saying that F equals MA kind of is the governing law, that makes some assumptions, and I don't feel bad about that. I think that is, that limits the things it can describe, but it also gives power to my ability to, in terms of writing algorithms, but even in terms of generalization and other things, right? So it says, it makes this, so neural networks are general purpose function approximators, and they're good for that. It's an important thing to have. But a physics-based model makes a few specific things, saying I will not be able to describe things where energy is not conserved, because I'm putting in as a conservation law, conservation of energy. Mass is conserved. These are priors that you're putting in, strong priors, which limit the class of models you can describe, but also allow you to generalize more broadly. So you have to just decide, I think, and that's the name of the intuitive physics game, is how can we walk up and down this, use the structure when it makes sense, but not give up the structure, too quickly. And there's things like spreading peanut butter on toast where I know mass is conserved, but I don't know how to use that efficiently with multi-body equations. So there's plenty of work to do for you guys in the middle. Let's just, limitations of multi-body parameterizations, just to name a few specific ones. So to be clear, when I'm talking about the multi-body, we've been talking about our state representation is positions and velocities. And our parameters, we saw in the last lecture that the parameters are only of a few types, right? They're the inertial parameters, mass, moment of inertia, center of mass, location, and then the kinematics of the multi-body tree. So the location of the joints relative to each other and stuff like this. These are the parameters of the multi-body family, as typically written, which doesn't immediately address I think we can grow them towards it, but it doesn't immediately really address perception. Why? Because the joint positions and velocities of the multi-body state may or may not be observable, for instance. We don't have any notion of that in this set of equations. That's an easy one to say. I think an important one that I almost feel bad about, like I feel it's almost a historical accident that We don't really, we have ways to talk about uncertainty over velocities or uncertainty over positions, but we don't really have uncertainty over geometry. Like somehow, almost historically, we haven't really explicitly parameterized the geometry parameters in those equations and written distributions over them. And ML has been pushing us on that front, but I would say that's obviously important to multi-body equations, but somehow tucked in as a detail. It's typically assumed that we know the geometry. And for, like I said, for a robot, you kind of just get a ruler and measure the link length and don't worry about it. But when it's contact mechanics and the geometry influences your friction cone and whether you're in contact or not, those become vital to the time evolution of these equations, but it's surprising maybe that we haven't spent enough time thinking about distributions over geometry and the like. And building on that, I think the multibody, as we've written, I wrote multibody, but really the stuff we've been talking about is rigid body. Multibody could be deformable, but we haven't talked yet about deformable or fluids or I'll just say plus, all the non-rigid type physics. And maybe there's one more really big one I'll put in my list here is that this paradigm doesn't immediately give ideas about state abstraction or model reduction. So I'll try to fill in with some examples, some of those, but this is just kind of motivating why I'll take a couple deep dives today, okay? So what do I mean by that? So when I gave an example of chopping onions as a hard problem, right? I know that I could definitely simulate chopping onions. I could write the pose and velocities of all the onion pieces, but that's probably not the model I want to identify and use for planning and things like this. There should be some way when I'm chopping onions to somehow write a simpler version of that set of equations that still builds on physics, I would think, but doesn't have to have the entire complexity. Okay, so these are just big, maybe, there's things that I chose not to put in here, but this is maybe a big list of things that we could do better. Questions at the high level? Is it helpful to talk about the high level stuff? I mean, any questions at the high level? You guys can fire whatever. These are now we're getting into the deep dives of more boutique lectures, I guess. So feel free to ask off the cuff questions. Okay, let me take a slightly deeper dive into on this side and tell you a few things that if you're willing to put even more structure in, I could have picked tabular or linear, but I'll pick linear first, okay? And I think there are lessons, because we have such good algorithms for this, there's a few more lessons that you can take from the linear case that will apply all the way. But they're just so hard to think about over here. And they're so clear over here, okay? So let's just think about what it would look like to do linear system ID. And I'm going to do it at a level that gives you some details, but also, I'm trying to aim at the big points here. So in this case, the model class I'm searching over in state space form is always written like this, basically, right? Very classic form of the linear state space equations. V is just another, we typically distinguish between the observation noise and the process noise. So the system ID question here is given, again, data U and Y, find now A, B, C, and D to explain the data. Right? A, B, C, and D are matrices. They're the matrices that are the parameters. Those are my thetas. If I were to vectorize them, they'd be my thetas. And the solution is, again, as I promised, is very powerful, very clear, and it's going to go back to least squares. It's going to look a lot like the multibody in the simple case, and it's going to do more than the multibody good in the output case. So let's just remember in multibody, I assumed actually the data was U and X. I chose to say that I had positions and velocities, and I had torques, and I was trying to find the masses and inertias and lengths. Okay, so the analogy here would be, if I wanted to do a closest analogy to what we did in multibody, let's do a subproblem. Let's say, given U and X, find A and B. Okay, that's actually the closer analogy to what we did in the multibody. And it's going to line up just like, remember what we did in the multibody case? We took our data matrix, we took our parameter vector, and we did least squares to minimize the one-step error. And guess what? We can do exactly the same thing here, and it's even simpler because we've already written it in a linear form. Okay? So we're going to make our data matrix. Times our parameters. Okay, and the way I'll write that is I'm going to say, let's call it X, I'll call it X, what did I call it? I'm going to minimize over A and B. I'll write it in the rolled out form first, just to make it clear. What I want to do is I'm trying to use xn as the prediction and xn as the data when I write these things down, just to make my notation clear. Okay, I'd like to over all of my data n, I'd like to just find the A and B that make that least squares residual as small as possible. That's a one-step prediction error, and I just want to find the minimum of A and B. Is that clear? Yeah. And I can do that in the data matrix form by constructing a big data matrix. It's actually easier to write it. It's cleaner to write it as a couple data matrices. Let's make the data matrix for X, which is just, I'm going to stack all my, these are vectors, right? So they're horizontally concatenated to X. I'll do my U data matrix. And then I'll even though it's redundant, I'll make my X prime data matrix, which is just this whole thing shifted by 1. And then I can write this as a big least squares problem where I'm just trying to find A and B times the big matrix X and U minus X prime. Okay, so it's just another way to write that in matrix form. And I only chose to write it because it forms the data matrix like we did in multibody, and I just want you to see that connection. Okay, this was before my masses, my lumped parameters. Now it's my AB matrix. Okay, But if multibody was least squares, it's not surprising that linear is least squares in that case. Okay, and you can just solve that. This is just backslash operator in MATLAB or np.linalg. Whatever. Okay, that's just a simple least squares. And it has important properties that people understand very well, so that in my governing equations, if W, as long as W and V are uncorrelated with X and U, then this is an unbiased estimator, and people know a lot about, if you want to write a system ID paper and get it accepted at the SysID conference, you have to say all these things about asymptotic biasness, everything like this. It's a very mature discipline. The thing we hadn't done in multibody that we can do in linear systems is the input-output case. And if I don't even know what X is, I want it to discover X for me. That's beautiful. That's what we hope our neural nets will do, okay? But we can do it perfectly here. And doing it reveals a few details that really are general, okay? If we do the input-output data back to the given U and Y, the algorithm that I'll describe here is roughly, there's a few different names for it, but at least the most famous piece of it is called the Ho-Kalman algorithm. Okay, there's tools in MATLAB to do it. The one that'd be closest to what we're doing today is N4SID, if you care. If you ever go looking for it. That's the particular choice of realization we're going to use, okay? So this is more complicated because it's only a least squares problem the way I've written it. You'd like to say I'm going to just form a new data matrix again, but if I have this, I can't fit A and B in the least squares sense unless I have, until I have X. X is unknown. I have to somehow solve for X and A and B jointly. What's amazing is that you sort of can do that. And the reason is because as much as complex as that is, you can actually write Y as a function of the history of U's. So the first thing you have to look at is a model of the form this one's potentially biased, okay? But it turns out this is actually a history of U's. And this is a big matrix potentially. I can write Y at some long step as a rolled out version from that's still linear in the entire history of U's. Okay? This thing, if you remember, or if you connect back to when you learned signals and systems, if you took 003, or there's a couple different places you might have seen something like this, but this is the impulse response of the dynamical system. It's often called the Markov parameters of the model. The point is we can actually fit a model without solving for X that describes the input-output data, and this one we can just use least squares for. And then as a second step, we can try to recover A, B, C, and D that explains G. That's the magic of the linear system ID case. But when you do that, that second step, find A, B, C, and D to describe G, reveals some fundamental truths about system identification that I want you to see, okay? And one of the most important ones is that there are many different, the optimal solution of reconstructing G given A, B, C, and D is not unique. Fundamentally, it's not unique. It's only unique up to a similarity transform. That's, if you know your linear algebra, that's a precise statement, but it's super, I can make it intuitive in a couple examples. Okay, so if my goal in life is to model the input-output data, and I've chosen some state realization X on the inside, that's only a construct inside my system. It has no bearing on the actual data. So if someone were to come along and just say, I'm going to change x1 and x2, I'm just going to flip them, right? I'm just going to switch x1 and x2. That would change the rows of A and B, and it has to, and C, and it has to describe the same model. Is that clear? Example, if I were to permute x, let's say x1 and x2. Okay, so I can tell I don't have you guys. So does that make sense, right? So if you were to train a neural network, a recurrent neural network, an LSTM or something like this, okay? And it's got 50 hidden units. If you were to just change the 49th unit with the 30th unit, so just go ahead and just make a switch operation, right? It's going to describe the same, you have to wire the inputs, you have to change the inputs and outputs, but that's got to be the same model, okay? Why is that important? Because the optimization is not unique, and that it can actually affect the way you can't write an optimization that asks to get a unique solution to some complicated cost function, right? In linear system ID, we're very clever about knowing how to parameterize a family of models that are the same up to a similarity transform. And I don't know how to do that for LSTMs, but the problem has to be there. Okay, sorry.
So the permutation is not in time, but in the same time, like inside the future.
That's right. That's right. That's why I realized my notation was overloaded and I switched. Thank you. Yeah. Right? So if you just said, I'm going to just take those units, take the activation of those units and just flop them, it's the same model. Okay? That means when gradient descent's trying to go downhill to fit your recovery, it had to make a choice. I'm going to use neuron 32 for the red brick, and I'm going to use neuron 33 for the blue brick, okay? And that choice changes, the fact that there is a choice that it has to be make is bad for optimization, I would say, in general, right? That means you have to do some symmetry breaking. There's a place where gradient descent had to make a choice and go down one of these things. And in general, in more mature optimizations, we structure the parameter landscape so that it doesn't have to make that choice. And I would imagine there's a future, that we're not there yet, where we're parameterizing neural networks better so that it has this kind of topology. Okay, that's just an example. Similarly, the scale of the state variables x is unspecified. If I could take x and say I want it to be between -1 and 1. I could say x, I want it to be -10 and 10, -1 million and 1 million, right? And I'll just, if you give me an A, B, and C that has one of those values and you want to change it to the other one, I'll just scale up the input, scale down the output, and have exactly the same model. There's nothing in the problem that tells me how to scale that, okay? So in linear systems, we have beautiful understanding of Ho-Kalman makes a particular choice. It says, of the similar models, I'm going to pick the model that is well balanced numerically so that the controllability, I know I'm saying things that I haven't given you the background for, but that the controllability gradient and the observability gradient are balanced. And those are called the balanced realizations, and we understand a lot about them. And maybe it's happening in implicit regularization in the neural models somehow, but it seems absent from the discussion. Okay? So I really think that there's so many lessons from this. I know how to do it in linear systems, but that lesson has to be important for more complicated systems. That's not unique to linear systems. But the clarity of the math in linear systems allows us to make progress on it, and we have to shove that down the road. Okay?
What is that progress? I mean, do you think it's a simpler optimization problem, or what do you hope to gain from that?
Yeah, I mean, I think so. One way it might manifest would be different architectures, right? CNNs were a beautiful architecture for translation and variance in images, right? I can't tell you that for state space models in control, this is the right architecture to use. We haven't given you like the architectures that are obviously right. I think there's lessons that might say that you should have an architecture that is, I mean, we're seeing, equivariant networks and things like this. Like these kind of things, I think will potentially render the problem, some of the lessons from linear optimization up into the more complicated settings. Yeah.
I don't know if your question was also about like what will be the benefit. Is that part of what you were asking? Because I was also kind of curious. Like, do you think that the benefit of having these things included in the optimization and the parameterization, is it about like overall just better?
Good.
Like lower predictive error and generalization, or
Good. Yeah. So that's fair. So how would I measure the success of the neural network versions of System ID right now? I mean, I think they tend to be very successful in getting the training error low already. I think there's questions about how well they generalize or extrapolate. I think there's questions about how reliable the convergence is. I mean, I think we can almost always make them work, but if I knew it was going to work, I'd be in a different space. Right? So I think it's just levels of maturity of that and potentially extrapolation kind of benefits. Great question. Yeah?
How is it currently done in linear systems to avoid this issue?
Yeah. So you can ask the question that for all A, B, C, and D that reconstruct G, choose the one that balances, that is somehow balanced in some, so there's an extra objective saying, all things equal, I'd like the amount of control effort coming in to roughly be the same as the amount of observation requirement. I mean, it's very clear. It's controllability gradient and observability gradient. I'm trying to say it clearly, but there's a very natural objective that you say, I'd like basically my eigenvalues for one half of the problem to be the same as my eigenvalues of the other half of the problem. And that's a natural choice in the linear system setting. Okay, so let me just show you, like, the linear systems can't do everything. They're too weak of a model class, but they can do maybe more than you think. So let me just, as an example of like connecting to perception with linear systems, I have an example here of doing, imagine I have a two-link robot, a cart pull system, and I've got key points on it that I'm tracking. And you'd like to ask the question, so the cart pull is an interesting nonlinear system. If it's going through its entire state space, then you need nonlinear equations to capture it. But if it stays near a fixed point at the bottom or the top, then actually you expect the linear system to be okay. All right, so let me just sort of paint that picture. So I have my multi-body plant, my scene graph and everything. I've added a simple system which just takes the body poses and renders some key points. My little key point system, okay? So, and all I'm going to let the system ID, that's my output now. I'm going to let my system ID look at the key points and look at the U's. It does not know that this is a two-link robot that has position and velocity It doesn't know that it's coming from F equals MA. It's just saying, describe the input-output data. And if we think it's done a good job, then I would hope it kind of figures out that there should be about 2 states with two positions and 2 velocities. Okay, so this is the data I fed it. I generated a few rollouts of, I made a simple balancing controller just to keep it in the linear regime. But this is my little cart pull system. You see it's a little cart with wheels and a pole that could fall down, my inverted pendulum thing. But the pole's not falling a lot. I kept it in the linear regime, which is the limitation of this model. Okay, but that's what it has to work with. It says, given that view, find me a model. I don't know what the state is. Come up with a state realization that describes that input-output data. Okay, and I run the Ho-Kalman algorithm on it. And I get this is my input-output data. Oh, that was just waiting for me to press the next one. Okay, this is what my impulse response looks like, which is the data's impulse response and the model's impulse response. It did a pretty good job. And what's important here is that I can solve for any choice of the number of state variables. I can ask, what's the best A, B, C, and D? Okay, and it'll tell me what's the reconstruction error given a choice of, I did 0 states, 1 state, 2 states, 3 states, whatever. Okay, and what you see is that there's a lot of error if you have 0 state. It's not an input-output static map. If you get 1 state, it gets better. 2 states, it gets a lot better. After 4 states, we know the real nonlinear equations have 4 states. After 4 states, you have diminishing returns. Okay? So something good in the linear regime, we have tools that find the state representation, even a nice state representation by some understanding that figures out that that data came from a system that has 2 degrees of freedom with 2 velocities. Sorry, yep.
So why does it still improve when you add more states than it actually has?
Because the system's not linear, and because it's it has noise and other things, it could try to start explaining the noise, right? It's not that it can't do a perfect reconstruction given the input-output data I've given it with any number of states actually. But did I make that point well enough? Maybe. This is what I'd like LSTMs to do too, and we do see that sometimes. You can go in and you can look at the behavior of a recurrent network and try to identify what a particular state it's doing. It's just more complicated. And here we can understand it.
So Ross, I'm just thinking about the dimension. So given y and u,
Mm-hmm.
those are observed,
Yep.
the dimension of d is fixed.
The dimension of D is fixed, yes.
And but for the rest, how do you actually parameterize?
So the reason that I made that plot is that every time you can solve it for any particular choice of state. So I say, try 1 state. Then I have a clear parameterization. I can solve the problem. And because it's only 1 variable to search for, this is what people do in practice, even for really complicated systems. You can just say, how many states am I going to give it? And you expect a diminishing returns. And at some point, you say, I've got a good model at 4 states. Okay. Do people like this version, or do you want to see like robots pushing soft things around or something? I've got one more lesson from the linear case that I could do, or I could skip to the graph networks and stuff.
Does the number of key points matter in this example?
I think the number of key points it's relatively insensitive. Of course, it'll at some point, but it's sensitive in a particular way in which the noise floor, basically. I think the key points, for instance, at the end of the pole are probably doing a lot of the work in some sense, right? And if I took away the ones at the bottom, it would be, but the way to think about that is because of the signal to noise ratio between the the noise I'm injecting in both measurement and process, compared to the magnitude of the signal, how much it tells me about the dynamics. Yeah, I suspect I could just do it with half the key points and it would be fine. Yeah, especially if I kept the ones at the top. Yeah. What do people want? What do people want? Choose your own adventure. Task relevant states, approximate information states. How do you learn a state that doesn't have to reconstruct all the observations? He votes for that, and we have one vote, so I guess the majority has it. Okay. Silence doesn't pay. Okay. Let me tell you quickly about task-relevant models, okay? It's not a closed discussion in linear systems by any means. It's not, so I would say in input-output reconstruction, we're pretty mature. This notion of learning task-relevant states is still pretty new, and I think we're going back and understanding it in the linear system setting in order to go forward with the more complicated. Okay, so this is my standard model, right? But if you think about what U and Y are in our robot context, right? U might be torques, Y might be pixels, and there's a bunch of people in the state representation learning world that have nicely told the story that that reconstructing the observations is more than you need to solve control problems. Okay, so this is one of the ones I think that makes the point nicely. So Amy Zhang has a nice line of work where she said, okay, if you're an autonomous car, there's features of the pixel space that just are not relevant to driving, right? And there's others that matter very much, okay? If you're trying to learn a model for decision making, not for just prediction, then it might be that predicting that there's a barn or a tree is you're kind of wasting state and making your problem harder, potentially. It might be very hard to construct that, right? So maybe an extreme example is that you're just trying to solve one of the RL gym examples, and someone's playing a movie behind the cheetah, okay? And if your task is to do model-based RL for something on the cheetah, you shouldn't try to reproduce the Gone with the Wind or whatever's playing in the background, right? That's just a lot of work to reconstruct those. It would require a lot of state. So how do you not do that, right? The prediction cost, the standard sort of reconstruction cost from system ID asks you to reconstruct all the observations. That was always the classic framing. So there's a lot of interest and some nice work, I think, on learning task-relevant models. And I have to pick a slice to tell you, but I think the one that complements the linear story is a particular version. Now, I know some people are working on things like student-teacher kind of models of this. That would be one way to, well, I'll make that connection when it makes sense. Okay, so what makes a model good for decision making, right? What makes a good X? Ultimately, what makes a good X is if I can write my optimal policy as a function of X, right? The real objective would be if someone told me what the optimal policy was, I would like to find an X that captures enough information about the task so that I can make, as a function of X, optimal decisions. I think that's a very natural way to say what would be a task-relevant X. And the claim from that picture is that knowing where the barn is should not affect my policy. Therefore, it doesn't need to be an X. Knowing where the road is very much decides this, and so it must be an X. So this metric of saying X should be sufficient to make optimal decisions is a nice metric for task relevance. The problem is, the way we're doing this so far is that our goal of system identification is so that we can build a controller. There's a chicken and the egg problem. If you have to, someone has to tell you the optimal controller, then this objective directly is tough. People try. People will say, like, I'll do, this is where the student-teacher kind of idea comes in, for instance. There's ways where people will try to find surrogates for that optimal policy and find an X that is sufficient for predicting it. But there's a nice idea, an interesting theorem, and I like thinking it through in the linear systems case. In the reinforcement learning, dynamic programming, optimal control world, I guess you guys know all those, so I can say RL, DP, optimal control world, okay? It turns out that if X is sufficient to predict the one-step reward, then it's also sufficient for making optimal decisions. That's pretty cool, okay? If X is sufficient to predict the one-step reward or cost, then it's sufficient for this problem. Okay, so an interesting way to think about that is that really I have a system going on here, but it kind of has two outputs, right? I have the full observations, and I also have, at every n, I have a reward function, a scalar reward function. This might be high-dimensional images, but this is always a scalar reward. And it turns out, theorem, if you have a state inside here that can perfectly predict reward, then building a controller based on that state can perfectly predict the optimal policy.
Is reward a function of X or function of X and U?
The reward is a function of X and U in general, yeah.
So once that reward is like sufficient to predict, once that reward the ability to predict any actions in that state.
That's a different thing. So I'll just repeat it. So Leroy says, well, since reward is a function of X and U, then that doesn't seem surprising. But X is high dimensional. I'm only giving you a scalar, right? I'm giving you a scalar observation. And it's not clear that you can go from a scalar observation back to a huge state, internal state.
So my question was, is one-step reward the reward on that state or the reward on that state and any action that it can take to that state?
It's only the rewards you observe during the rollouts in system identification. So I've observed, 10 rollouts of my system, and I got data for U, I got data for Y, and I got data for R. I don't have some magical ability to see what reward would have been at different states. Mm-hmm. But the model has to be able to predict. So this is okay. Maybe what your point is that this is a big requirement in the sense that it has to be able to predict the reward for all X's and all U's. That's true. Yeah. But the good news is that it doesn't require solving the optimal control problem. Right? That solving the optimal control problem, once you have this state, is sufficient to actually, you can solve it after. You can first find your state representation. So actually, the proposal that this suggests would be that what you should really do is think about task-relevant models as doing system identification, but instead of doing it from predicting y as a function of u, you should try to build a system model that just predicts the reward as a function of u. Okay? Now, where this gets more complicated is that this theorem says I'm able to perfectly predict reward, and then it's sufficient. The interesting case is when this becomes an approximation, and there's a nice paper called Approximate Information States. We always call it AIS, okay? Which talks about putting a bound on how well you can perform given a bound on how well you can predict your outputs. So it goes into the approximation case. This is also related if people have heard of bisimulation. Bisimulation tries to do this kind of with state aggregation, but if you've heard of bisimulation, there's a nice line of work thinking about that too, saying I'm going to combine two states in my MDP, for instance, if they are identical with the view of the reward. Okay, that's only useful if you've seen it. So, okay, so that's a super powerful idea, and there's nice work now about saying what can we understand. So once I started thinking about this kind of idea, the immediate question I asked is, can we understand how that works in the tabular case? And we've got a paper on that recently. And can you understand how that works in the LQG case, the linear case? And we submitted a paper about that at midnight last night. This is like ongoing. I'm super excited about these ideas. Okay. But that's a very different and exciting, I think, view of what the model should do. And I do think naturally the idea of a task-relevant model is one that should be sufficient to predict the reward. Okay? But this question of sort of state representation is really the first fundamental question of in my mind of what I mean by intuitive physics. It's funny because Josh Tenenbaum sort of coined the word intuitive physics, or he popularized it certainly. It came from cognitive psychology. He popularized it in our world. And he and I will be having a conversation about intuitive physics. And about halfway in, we're almost always, because we do this every once in a while, almost always we realize halfway that you don't mean the same thing when you say intuitive physics as I mean when I say intuitive physics. Okay, but for me, it's the search over models and this question of how do you find states? And then the second question is control with these approximate models. And you can't decouple them completely, in my mind. I think the quest is finding representations that are rich enough, that are task relevant enough, that are tractable enough, both for system ID and for control design. Okay, so let's walk a little bit more back and forth on that line of model complexity, okay? I want to tell you quickly about this work that Danny Dreiss did very recently, and I just think it's awesome. And it's just another example on the spectrum, okay, of complexity. So let me set that up with, again, we talked about the various limitations of multibody. One of them was not being able to talk about deformable objects or not being able to talk about geometry. And Danny's work was trying to address that shortcoming. And he did it with NeRF, compositional NeRF, okay? So let's say a very popular approach in visual dynamic learning here is to say, I'm going to take an image in, I'm going to define my state X, with an autoencoder kind of framework. I'm going to predict an image out. This would be do people know what autoencoders are, roughly? If you try to learn a neural network function, let's say this would be my encoder. This would be my decoder over here. And my state is in the middle here. I'm going to try to compress my image into some small latent vector x, and so that I can reconstruct the image. This is very much not the task relevant case. This is the reconstruct the observations case. And it's also missing the dynamics that I love. But this is a very common approach. And the reason it's nice is that you can train it directly on images first and then think about the dynamics later. But so once you have that, that representation, and by the way, in this world, everybody calls it Z, not X. That's the latent state, I'll call it. Z, and then people will try to learn a dynamics model on that as a second pass, for instance. And you can imagine trying to learn that parameter to reconstruct the inputs and outputs with Z, okay? But that has no notion of physics in it. That has no notion of there's multiple objects in the scene in it. There's no notion of there's no structure that's coming from geometry. So there's a line of work. It started with, for us, it started with Yunzu Li, who started using some of the geometric reconstruction, the NeRF, the volumetric reconstruction as the decoder. So these neural radiance fields here are a choice, are one way that you could imagine going from some vector representation up to a complete image by these volumetric reconstructions, okay? So Yunzu and his collaborators started coming up with latent states that had this extra requirement that they needed to be able to do not only reproduce the image, but also do novel view synthesis, and they used this neural radiance field as a decoder. But Danny thought, what's crazy about that is that if you have multiple objects in the scene, you're trying to compress all of them into a single vector, a single NeRF. Obviously, there's multiple objects moving, and they should each have their own sort of geometry representation. So let me tell you how it, what it does, and then we'll spend a little bit more on how it works, okay? So this is a simple manipulation pipeline. Perception wasn't the major focus. We made all the objects, Danny made all the objects bright colors so that masking and segmentation were easy. He could have trained a mask RCNN on this, but he just said, I'll just make the shoe red and the other objects very colorful. And then he wanted to generate a data set of pushing, okay? And he just took his robot, put a blue cylinder on the end, and started just moving it random vectors across the table and shoving the objects around. And he did this in two steps, right? So the first step was, I'm going to look at the scene and I'm going to break it down into individual models based on just the mask. So mask RCNN could have done it, but we could do just color-based segmentation here. I'm going to group the pixels and say these pixels for the purple this represents one view of that object, and I'm going to train a NeRF effectively on just that object. And I'll do the same thing. I'll treat this one image as a view, observed view of the original shoe from this angle, and similarly and so forth. Okay. here. Okay, yeah, and then he's going to train a model here that's using the NeRF as its underlying geometry representation in order to do this sort of reconstruction, and he's learning a model on the NeRF that can predict forward dynamics. So this is the rendered from the current observation. This is the output of the model when you started from the initial observation and you just simulated forward. The prediction error, the objective of our system ID, is roughly the difference between those two rendered images. And in my mind, that works incredibly well. Just as an ability to predict complex unknown objects forward in time with physical interaction, I was like, what? Yes?
Is the control inputs on the robot provided, or is that being predicted?
In the data generation and this initial thing, he's just open loop, straight line trajectory. Well, I mean, it's closed, position controlled trajectories like this. Just something that I think he would, okay, so it wasn't completely random. He would just take like the center of mass of the colors and just move through them.
I guess, but I mean, like, it's predicting the motion of the end effector from the initial observation.
Yes. Yes. Yes, this is a long-term prediction. Yeah, yeah. Okay, and it has the property, this is what you'd expect out of the compositional version of the architecture, is that it has the property that you could put new objects down that have never interacted with each other, and it's surprisingly able to generalize fairly well. It's not perfect. You can easily find artifacts in the rendered images, okay? But it's actually able to predict how novel objects that have never touched each other before would interact. This is also not a super dynamic regime, but it's a contact-rich, manipulation-relevant regime. Okay? And it even works for deformable objects. This is, yeah, here we go. So this is I don't know, party snake or something. Poor Danny. Danny was a visiting student here who arrived 2 weeks before COVID from Germany. And so we mostly collaborated remotely, and he went back to Germany and did all his experiments in Germany, so I only know these through the video. Okay, so that's a forward neural network model that's predicting long-term deformations of a deformable object that it had never seen before. Okay, so that's cool. And the way it works is I only mean this as one example of a wider class of interesting models that are, from just a deep neural network doing everything to like, I'm going to put in a little bit of structure. I'm going to admit that there's geometry. I'm going to admit that there's some sort of contact mechanics, but I'm going to try to leverage the power of learning a network, okay? So the way it works here is that for each of the images, this is an image with multiple objects in it, there's going to be a mask for each of those objects, and there's going to be a trajectory of those masks. Each one of those masks gets shoved through an encoder, de-rendered with a NeRF into a new image, and you learn your latent vectors in this way. And then you learn a dynamics model using a graph neural network as the representation, because we don't know how many objects there are going to be at runtime. You want to be able to assemble new models, so we use a graph neural network structure where the neural net weight are on the edges of the graph, okay, to do long-term predictions. And you can then test, for instance, by just de-rendering a future observation, and that's what we showed you, the reconstruction from a long-term simulation versus the reconstruction from the original, or I could put my initial thing in, render to Z, get an image out. That would be the instantaneous reconstruction, if you will, or I can do the long-term simulation. Okay, so you take your scene observation, you decompose it. You actually have to give not just the actual pixels of the object, but a little bit of a buffer around it in order for the NeRF to learn about the edges of the objects and stuff like this, okay? And then there's the prediction. And it's only a very small, so the one way that there's a little bit of physics bias, if you will, is just that it's object-centric, that there's a mask RCNN type network that's doing segmentation and saying that there's some number of objects and I want to learn different models for different objects. The second way is that when he makes the graph neural network, whether you put an edge in or not is dependent on whether the geometry representation overlaps. Those are the only physics-based biases in this model, but they're enough to give stronger, long horizon predictions. Right, so he did ablation studies, for instance, where you said, I'll put all of the objects in the scene and I'll assume that they can all interact with all of the other objects. And he compared that to say, okay, well, I can take my NeRF representation and just query, are they overlapping? Should there be any forces that interact between those two? And that's a little bit of physics bias, okay? And it gives you these sparser adjacency matrices, and naturally it's an easier function to learn and to roll out more stably into longer horizons. Okay, and so, surprisingly long, in my mind, surprisingly long long-term predictions. And you can find errors, and bricks will slowly kind of fade into different colors and other things, but it's surprisingly good. One open loop prediction. Oh, I'm sorry. So every time the video resets, it's the next one. Yeah. Yeah. And then Danny and everybody who's building these types of models have ways to do basic planning and control on top of them. I would say we can talk a little bit at the very, very end. It is almost the very, very end about the state of the art of those planning and control algorithms, but they're still weak, I would say. So he did a RRT in the latent space in order to do this, and he considered that the weakness of the work so far. It's just future work. Okay, but that task, just to make it clear, he tried to push the blue squares into the blue region, the yellow squares into the yellow region, but the model originally, before training, had no idea that there was what a cube was, what the dynamics of a cube was. There's no sense of mass or anything directly. It's all embedded in the neural network. One other thing I just have to at least mention is that there's been a lot of nice work on using particle representations. So this is, we talked about rigid body representations, but if you want to do deformable objects or fluids or other things, another choice that Yunzu's done a lot of nice work on, and other people have done a lot of nice work on now, is to just represent your relatively complicated thing with a bunch of fluids, a bunch of particles. And some of the physics-based simulators that you see out there actually do use particles, not rigid bodies. So NVIDIA Flex is probably the most famous one, right? But they have great animations of semi-rigid things, rigid things, fluid things, all interacting beautifully by simulating bazillions of particles on a GPU, right? So Yunzu was asking, well, can we use that as our underlying representation in a neural network? And he's done a beautiful line of work thinking about these kind of things, where he would, again, use the graph neural network, and he would add the edges in the graph based on not only the location of the particles relative to each other, but if they were particles associated with a rigid object, they would have a different graph topology and a different set of edges that would somehow impose the rigid. If they were deformable, if they were fluid, they all had slightly different underlying elements. And then he did these long-term rollouts of really complicated things, right? Of objects that could blend into one big object, of rigid grippers. We had a bunch of things that were like sticky white rice that he was trying to squish into shapes up in the lab, okay? Of pretty complicated fluid simulations that could be represented again in a neural network and then used as a surrogate model for planning and control. So those are just two instances on this landscape of using a bit of physics, and putting in more structure that can potentially generalize more. So I was telling Anthony as we walked in that I feel like I could talk a bunch more about these kind of things, especially because I didn't say anything about how you do control with these, and that's another whole topic. So let me just call out very quickly a few ideas about that. Once you have a big model that's a compositional NeRF or a particle-based graph neural network or a feed-forward neural network, then there's a big question about how do you do planning and control with that. And the answers are are surprising to me, but a lot of times the answers are, even though they're differentiable, people do black box rollouts, black box optimization on that, and there's, I think, some subtle reasons that people have studied for why that is. partly just because GPUs are good, okay? But that seems to be the state, and they're strong algorithms, but they tend to work with relatively limited planning horizons compared to what we're used to with physics-based models. Relatively short planning horizons. But the other thing that I think is almost more central to these is that neural networks are able to represent almost anything, and the training error does go to 0, but they tend to predict very well near the training data and do arbitrary things away from the data. And if you write an optimizing-based planner against that, then it's very easy for your optimization to try to exploit the things that your model's not good at. So I think the same way we had keys to making a rockstar in behavior cloning demo, I think the keys to making a rockstar learned model control demo are to add in a few extra heuristics and costs that force you to stay close to your training data. And in general, physics-based models, you tend to say, I remember I moved the ball once and I was able to throw it across, well, Jean-Jacques was able to throw it across the room, right? That's extrapolation. It's beautiful, right? The neural network is going to be able to model almost anything around the data, but it has a harder time extrapolating, partly because we haven't put any structure in. Why should it, right? So, okay, that's a quick blast through some intuitive physics. I think it's a huge, open, exciting research topic, and it's bringing in people from pure ML and people from robotics and people from all kinds, and perception and all that. So maybe it'll bring in you guys too. I will see you Tuesday.